Cool. Welcome to the reverse linked list. So we are given a singly linked list and we should reverse it and return that reversed list, right? As simple as that. So in our example, we have a linked list with 5 nodes and the values in the nodes are 1, 2, 3, 4, 5. And we have the links, as you can see here. And of course, the link from the last element is to null. So we can denote that, there is no more nodes afterwards. And we will return 5, 4, 3, 2, 1. So the reversed list obviously has the same number of nodes as the initial one, but the values in the nodes are basically reversed. So one thing I should note about this is that we only care about the values in the nodes, right? So we don't care about, if this node should be exactly the node that is here. And by exactly, I mean the exact same memory address, right? Because this node 1 is going to be stored somewhere in a memory address, right? This is its memory address. Cool. Well, we don't need that, this one to also point to the same memory address. This is a very important detail. You only want a node. This one could point to a different memory address, no problem. But the point is to have value 1 stored in that memory address. That's it. So the memory addresses can be totally different than the initial ones, but the values should be the right ones. The first one here should be the last one here. The second one here should be the, second to last one here, and so on and so forth. Cool. Now that we know the statement, let's think about this problem. This problem is actually similar to a problem that we have previously solved, which was on strings and asked us to reverse a string. So yeah, my first initial thought was like, okay, I should do the exact same thing here. Maybe I need, a pointer, a node, which is going to point initially to the first one. And I'm going to need another pointer here, last, which is going to point initially to the last node. And all I have to do is just swap the values of first and last. And then, move first 1 step to the right, move last 1 step to the left. This would definitely be a correct solution. I mean, there is no problem in keeping the existing nodes at their memory addresses and just swap the values that they store. Awesome, that's cool. But the problem here is actually moving these pointers, these indices, first and last. And to be specific, the problem is not when we want to move first 1 step to the right, because we know this link, right? If this is first, this link will always be, first dot next, right? So we can always move to the next node. We can always move first to the right. But the real problem here is that we want to move last 1 step to the left. And because this is only a singly linked list, it's not a doubly linked list where we also had, a previous link which pointed to the previous node. This can't be achieved. We can swap the values of first and last. Very good, in constant time. We can move first to the right, very good, in constant time, but we cannot move last to the left as we don't know or we don't have a link, to the previous node. So this solution is not going to be the right one. And this is the interesting part about this problem. Instead of following the natural thought of swapping values, which I try to do, we have to actually change the links. Think about it. If I find a way to replace each initial link to its reversed one, the problem would be solved. For example, if I can remove this link and now have this link and then remove this link and add this link and remove this link and add this link and also remove this link and add this link, what I'm going to have here is a singly linked list which actually has the same values as the initial one but in reversed orders. And the head of this list is going to be the node that was the tail of our initial list. And this is it. That's all I need to do. Now we need to find a smart way to implement this idea, right? Well, it's not actually that hard. Let's start again with the initial list. What you should do is always have a pointer to, the current node and another pointer to its previous node. Because in order to remove a link and add another one between 2 nodes, we actually need to know what are the nodes, right? So we will store a pointer node which starts from the second node and another pointer previous node which will always be equal or will always point to the previous node of node, right? And now that we know these two, it's very simple to remove the link and add the new one. For removing the link, all we have to do is set previous next to be now null. Obviously null or none depends on the programming language, but you got the idea. And now I basically remove this link. In order to add a link from node to prev, all I need to do is set next of node to be equal to prev. I'm gonna do this and then shift node and prev one step to the right. So what's the next? Node is gonna be here, prev is gonna be here. Again, we do this too, so we now have removed this link and we add this link. Node is shifted one step to the right, then this link is removed, this one is added, and so on and so forth. We are going to do this as long as node is of course not null. Because at some point, let's say we had more nodes here, we will have the, last node, and node will be here, and previous will be here. We'll do this too. So remove this one, insert this one, and then shift them one step to the right. So node will actually point to null, because as this is the last node, as you can see, it links to null, and previous is now going to point to the last node of our linked list. And at this moment of time, we know we need to stop our algorithm, and the new head of this reverse linked list is going to be the previous node. And this is exactly the node that we are going to return. Now let's see the code and analyze the time complexity. Awesome, and here is the code. So as you can see, I initialize prev with head, the first node, node with head.next, the second node, and while node is not null, what I'm gonna do is remove the link by setting prev next equals null, insert the new link by setting node next equals prev, and then of course I need to update prev and node to go to the next, two correspondent, two consecutive nodes and change their links. So prev will become node and node will become node.next. I know I have a mistake here. It's very, very good if you noticed it. That was the test. But if not, we're going to discuss about it. And of course, in the end, I'm just going to return prev, as this is going to be the, the new head of the reverse list. Now, let's see about that mistake that I've made. The mistake is actually here in this while loop. And I want to take a look with you again at how we change the links and how we shift prev and node to the right. Let's say at some moment of time, we have two consecutive nodes, right? The first one is prev, and the second one is node. Let's actually see what our code does. So, prev.next equals null. Okay, so what's going to happen is that we remove this link. It doesn't exist anymore. Then, node.next equals prev. So now I have my new link from node to prev. Okay. Prev equals node. Okay. So now prev is being moved here to be ready for the next step. And node equals node.next. And here is the problem. You might expect that node equals node.next, to have pointed us to the next node. But that's not happening because we've already set node.next equals prev. So now the link that we had here was actually removed and this one was added in its place. So this is a problem because node, instead of moving to the next node, it will actually move to the previous node. And on the next step, on the second ever step, prev is going to, node and prev basically switch places. And we don't want that. One way to do this is before removing or adding any link, store another variable to remember what was node's next node. So let's have a variable node next, which will be set to node next. Have this instruction here before the others. And now, of course, set node to be next node. And everything should be fine now, right? Well, not really. Always be careful when manipulating the links of a singly or doubly linked list, because once you do that, you might be affected in the future. For example, here, you won't have the right next node anymore. But there is also one more problem which we should talk about. So let's write this code that we have for now and simulate it a little bit on a simple example to see what I mean by that. This is how the new code should look like, right? Let's simulate it on this 4 nodes linked list. So prev is initially pointing to head. So here we have prev. Node points to the next node, which is here. So this is where node points. Then, while node is not null, which happens? Next node is going to be node next. So this we are going to have next node. Awesome. Prev next becomes null. So we basically removed this link. Okay. Node next equals prev. Node next, which was this link, it pointed to next node. Now it's gonna be changed to be this one. Node next equals prev. Now we have this link. Prev equals node. So now prev is going to point here, right? And node will point to next node. So now node is going to point here. Awesome. Okay, cool. Everything seems quite okay so far. Node is still not null. Okay. Next node is node next. So this is next node. Prev next becomes null. Whoops, we have a problem. Prev next was indeed this link, which is good. It should be present in our reversed linked list, and now we are about to make it null. That's not good. We just removed a link that was perfectly good. Node next equals prev. This is okay. We basically, change the previous link, which is from 3 to 4, to be now from 3 to 2. This is good. Prev equals node and node equals next node. Cool. So this is prev. This is node. And of course, we are going to continue. Next node is node next. So next node will actually be null now, right? This is next node. Prev next is null. So once again, we are going to remove a perfectly good link that we have just added. That's not okay. And of course, node next equals prev. Prev is node, and node will be new node, which will be null, and we exceed the algorithm. So as you can see, the first 2 links that we have added, which were perfectly good and should be part of our solution, we have then removed it on the next iteration. So this line of code, prev next equals null, is the one that did all this damage. So now I'm thinking, maybe I don't need to have this line of code, right? Maybe I shouldn't. Let's take the example again and simulate it without this line of code. Again, the initial linked list. Prev is initially head. Node is head next. So here is node. While node is not null, it's not. Next node is node next. So next node. Node next equals prev. So now, instead of this link from node to next node, I'm gonna change this link to be this one. Okay. Prev equals node, node equals next node. So now prev is here, and node is here. And we continue. What's gonna happen? Node is still not null. Next node will be here. Next node. Okay. Node next equals prev. So instead of this link, I'm gonna have this one. Okay. Prev equals node, node equals next node. So prev is now here. Node is now here. And we continue. Node is still not null. Cool. Next node is going to be pointing to null, obviously, right? Node next becomes prev. Okay. So the link to null, right, is now going to be to the previous node, which is good. Prev equals node. So this is where prev should be, and node equals next node, which is here. And now node is null, and we finish the algorithm and return prev. And as you can see, this list is almost fine. There are just 2 more changes that need to be done for this final list to be indeed the answer. And these 2 changes are as follows. First of all, we need to remove this link as it's not good anymore. And second of all, the first node, which now is gonna be the last one in the reversed list, should point to null. So actually, we can achieve these 2 changes in only one line of code. And that line of code is going to be head next equals null, so we set it to null, and it can be placed here. And everything will work fine. Let's add this new line of code and simulate once again the algorithm to see indeed that the list is right and finish the problem. So now prev is head. Cool, this is prev. Node is head next. Cool, this is node. Head next equals null. Okay, so this link is being replaced by a link to null. So here we have null. Awesome. While node is not null, which happens, next node is node next. So this is next node. Node next becomes prev. So we have, instead of this link, this is going to be replaced by this one, which is perfect. Prev equals node, node equals next node. So prev here, node here. Node is still not null. Next node is gonna be this one. Node next equals prev. So this link is being replaced by this one. Awesome. Prev equals node, node equals next node. So here I'll have, the new prev and the new node. Node is still not null. Node next equals prev. So the link which actually was here to null, right, because that was the last node, is not going to be present anymore, right? And the new one is going to be this one. Perfect. Prev equals node. Prev is here, and node equals new node, which is null. Now the node is null, we exit the while loop and return prev, which is indeed the head of the reverse linked list, which is the correct one. And that's it. Now let's think about the time complexity. Well, as you can see, assignment, assignment, assignment. All of this constants. While node is not equal to null, checking this is a constant. Now, only assignments, constant, returning a node, constant. So the real question is, how many iterations does the while loop do? Well, it's pretty simple. Node starts from the second node and goes all the way until null, right? So the number of iterations is actually going to be n, or n-1 to be more specific, n-1, let's say, where n is, of course, the number of the nodes, right, or the size of the linked list. When you are asked for the time complexity of a linked list, you can say to the interviewer that n is the number of nodes, and if we denote n the number of nodes, the final time complexity of the algorithm is going to be indeed big O of n. Every node is traversed at most once, and we only do constant operations. What's the memory complexity here? Well, as you can see, we use the exact same nodes. So we don't create duplicate nodes or other nodes. This is good. We use the exact same links, but we basically reversed their directions, right? And of course, we have a couple of variables which don't count. So the memory, the extra space complexity, the extra memory complexity is big O of 1. And this is the solution. And the conclusion here, guys, is that when solving what seemed to be a simple problem for the linked list, don't take it for granted and don't assume that I just iterate through the nodes, I, manipulate some links and that's it. It's going to be fine. It's going to work. Let's write the code. No, please just take your time. Take at least one example on paper and really make sure that the way you manipulate the links or maybe the nodes is the right one, because as you can see, it can get very tricky because manipulating one link can affect our solution a lot. For example, here we needed what was previously the next node, and now we have set it to another node, so it's not going to be the right one. Or for example, removing a link, you might observe later that you're actually going to remove the links that you've just added because you've changed them. So yeah, always double check, take an example, solve it on paper, and when you're sure that for your example the algorithm works, you can write the code.